Hi, my name's Charlie Hoyt, and I'm going to present our manuscript entitled A Unified Framework for Rank-Based Evaluation Metrics for Link Prediction and Knowledge Graph. Equal credit for this work goes to Max Bauerndorf, and big thanks to Mikhail, Volker, and Ben for their supporting contributions as well. So most knowledge graph embedding models, like Dismalt and Transy, are trained and evaluated on the link prediction task. And during evaluation, a rank Ri is calculated for each of the n entities in the knowledge graph, typically by comparing known triples to sampled negative triples. The three most common summary statistics of these rankings are the hits at k, mean rank, and mean reciprocal rank. The hits at k is the average number of ranks that are lower than k, which is useful in situations like showing the top k results of a search. However, hits at k doesn't differentiate between close misses and far misses. The mean rank is defined as the average rank, which better reflects the full distribution of ranks, but is biased towards larger ranks and susceptible to outliers. And finally, the mean reciprocal rank applies the inverse to each rank before taking the average. It's biased more towards smaller ranks and doesn't completely regard the bigger ones, like hits at k. So despite their ubiquity, there didn't already exist a theoretical framework for formulating these metrics that could help us reason about their different advantages and disadvantages. So here we're proposing a general form with three parts. First, there's a pre-transformation function applied to the ranks. In the case of hits at k, this is the indicator function. In the case of the mean reciprocal rank, this is the inverse function. And in the case of the mean rank, this is the identity. Second, there's an aggregation function. In each of these three common metrics, this is the arithmetic mean, which is a special case of the generalized Holder mean, where p equals 1. Third is the post-aggregation function, which is the identity in each of our three metrics, but this will be useful later on. Interestingly, this general form also allows us to reformulate the mean reciprocal rank using the harmonic mean, a special case of the generalized Holder mean where p is -1, and using the inverse as the post-aggregation. Through the lens of these two Pythagorean means, we can better understand why the mean rank is biased towards large ranks, while the mean reciprocal rank is biased towards small ones, despite their codomains having different properties and being on different scales. So using this general form, we can better articulate four desirable properties for rank-based metrics. Since all of our metrics are defined with the monotonically increasing mean aggregation, it's convenient to describe these in terms of the pre-aggregation function. First, we want the optimal value of the metric to happen with a rank of 1, which is the best possible rank. This happens in the mean reciprocal rank and hits at k, but not in the mean rank. Second, we want the worst value of the metric to happen as ranks get bigger and approach the maximum possible rank. And so here we're using infinity as an informal shorthand for that. Again, the mean reciprocal rank and hits at k satisfy this. And third, we want the ranking function to be anti-monotonic, meaning that bigger ranks mean unique worse values, which is only true for the mean reciprocal rank. And fourth, most importantly for this work, is that we don't want the expected value of the metric to be based on the size and topology of the data set, which we denote as ni. There are several motivations for improving these metrics, and most importantly, enabling the better interpretability and comparability of results on different data sets. As an example from drug discovery, you might want to formulate a biomedical knowledge graph using different combinations of resources to generate better drug disease link predictions. But this would result in different sized graphs with different topologies whose evaluation results currently aren't readily comparable. Just to send this notion home, we simulated the evaluation across random data sets to show that the expected value and the variance of each metric increases with data set size, and show this on the first row of the chart. So inspired by previous work from Bauerndorf et al., we proposed three statistical adjustments that can be applied to all of the base rank-based evaluation metrics that change their statistical properties. And this works because we can assume that all ranks are independent and identically distributed random variables with a discrete uniform distribution. So the first adjustment normalizes the expectation to 1. This isn't super applicable to metrics like the mean reciprocal rank, where the range is between 0 and 1. Second, we propose an adjustment by both the expectation and the optimal value, which maps the best value to 1, the expected value to 0, and all worse values to negative numbers, bounded by a constant related to the expectation of the base metric. Finally, we propose an adjustment equivalent to z-scoring, in which the expectation is subtracted and the value is normalized by its standard deviation. And this works because of the central limit theorem, and it gives us a very simple statistical perspective to the results, which can also be interpreted using the inverse CDF of a standard Gaussian distribution. So each of these adjustments takes the notions of a base metric and helps them satisfy our original 4 desiderata that we started with. So overall, we've proposed several derived metrics from the 3 presented in the beginning, as well as some additional ones based on the geometric mean and alternative post-aggregation functions, which we're not covering in this presentation, but we detail a bit more in our manuscript. We've included detailed descriptions of the assumptions and the derivations for all of the following slides in the appendix of our manuscript. And we also provide implementations of each of these in the PyKeen software package, so you can get them right now using the latest version from pip. So as a case study to demonstrate these new metrics, we want to present how they can be more interpretable in practice. First, we reevaluated a few standard data sets with a few different flavors of knowledge graph embedding models. And there's a few major insights just from this one picture, focusing on the mean reciprocal rank. First, the base metric suggests that complex performs similarly on WordNet 18 RR and nations, but the adjusted metric and the z-adjusted metric show that the difference is actually more remarkable. Second, the base metric suggests that Tucker performs better on nations than on WordNet 18 RR, but the adjusted metric and the z-adjusted metric show that when improving comparability by adjusting for size effects, Tucker actually performs better on WordNet 18 RR. Both the base metric and the adjusted metric display an anti-correlation with dataset size that's not present for the z-adjusted metric, disregarding the smallest dataset for which there's a numerical behavior of the adjustments that's slightly erratic. And finally, the z-adjusted metric enables a direct comparison between the results on different datasets, while also giving insight into their significance by normalizing against the expectations and variance of the metric under random rankings. This adjustment reveals that the improved original metric on the 2 smaller datasets, kinships and nations, were actually less significant than the results on the 2 larger datasets, WordNet 18 RR and Freebase 15K 237, yet despite achieving better unnormalized performance. So because of the formulation of these adjustments, they are affine, which means they can be applied as a linear transformation after the fact. As a last remark, we pre-computed these values for all of the data sets in PyKeen in a few different scenarios so that they can be reused by anybody, even after the fact, regardless of how they trained and evaluated their knowledge graph embedding models, even with a different software package. So this data set's available on Zenodo under the CC0 license. So we've done our best to make sure that the work we presented is robust, reusable, and useful. All of the code and data are available through these links, as well as the surprisingly tricky derivations of the expectations and variances of each of the base rank-based metrics. Thank you for listening.